tomorrow will have on it some fill in the blanks. Now this, you should, yes, study chapter blocks, okay? Or chapter block, sorry. To do the fill in the blank. It has some free body diagram problems. You have to draw the free body diagram. And then it has a force board problem. It has a hanging sign. And like ramp style problem. Okay? So some combination of these. Not exact. Remember we did the force boards in class? Horizontal or vertical? I'll do an example of that in a minute. Okay? And move on? No? Yes. They're going to be what? I can't hear you. Well, there could be on the ramp problem and somewhat in the free body diagrams. Okay, so here's a problem for you. There's a system is in equilibrium, okay? And it looks like this. And that's in equilibrium. The mass on the table is 50 kilograms. So that's this one. And the mass on the ramp is 100 kilograms. Okay. So we want to find, and the angle of the ramp is 60 degrees, and we're interested in what is the coefficient of friction. Okay, so here's a ramp problem that has friction in it, right? So what's your first ideas when you look at a problem like this? Michael says draw a free body diagram. And we're not only going to draw a free body diagram for the red block, but we're also going to draw one for the green block. And then we're going to use the tension force to link those two up. Yes. Two frictions. Oh, well, hold on. I must have more information. You're right. it's the same on all surfaces. Thank you. Yes. So the friction doesn't need to be the same. The coefficient of friction is the same. You see the difference, right? That doesn't mean the friction is the same. It just means that the coefficient of friction is the same. Okay, so we'll have free body diagrams we'll draw for both of these and see if we can calculate them. So let's start with the 50 kilogram one. What forces do we have acting on it? We have Fg down. What's another one? Somebody? F perpendicular up. What's another one? Tension. Keep that blue. So what's another one? Friction. Okay, good. So we have those forces. Now on the green one, Fg, Ft, F perpendicular, the component of Fg in the plane, which is called F parallel, and friction. Now this would just slide down the plane, I'm assuming, if friction wasn't there, I think. I should see what the parallel force is real quick. Well, even so, yes, it would. If there was no friction, it would slide, because the downward force would pull this along. So the friction in both cases, so the motion of it would be like this without friction, so I know that friction then is opposed to that motion. So this way and up the ramp. Sometimes you have to do that because if you have something hanging off the side, it could be that it's going to pull it up the ramp, then friction is down the ramp. So you have to give that some thought, whether it's up the ramp or down the ramp. In this case, it's up the ramp. Yes, Austin? Which friction? No. The other one, though, yes. This one, yes. So let's see. We're going to sum the forces in both cases. So for the red one, we'll sum the forces equals 0. For the green one, we'll sum the forces equals 0. The red one is in the direction of this direction we're going to look at. And so in this case, since it's in equilibrium, the lefts equal the rights. What do we have going to the right? So Ft equals Ff. You see that? Now for the green one, the down the ramps equal the up the ramps. Right? So F parallel equals Ft plus Ff. Yes. Let's see what information we can get when we start filling out with the formulas that we know that some of this stuff is. Not really a sentence, but let's fill in what we know. All right, so F tension, we don't have a formula for F tension. It just comes out of the free body diagram. But friction, we know, is equal to mu times F perpendicular. So we could solve for F perpendicular because we also know from the sum of the forces up here that F perpendicular is equal to what? Fg, it's flat. So F perpendicular equals Fg equals 500 newtons, right? No. F perpendicular is 500 newtons. Ft equals mu times 500 newtons. How many unknowns do I have in that equation? 2. Well, so we can't solve it, right? What's the formula for F parallel coming over here? Julia. F parallel. Fg sine theta, right? So that's, we'll plug those in a minute. Ft, we don't know. What's the formula for friction? Okay, so Fg is 1,000 newtons times the sine of an angle 60 degrees equals Ft plus mu times F perpendicular, but F perpendicular is what? What's the formula for that on the ramp? Fg cosine Newton, cosine theta. So 1,000 newtons times the cosine of 60 degrees. Let's clean that up because it looks pretty awful right now, but it won't be too bad. 1,000 sine 60, 866 newtons. Mu times 1,000 cosine 60. Ooh, 500 newtons. Something I don't like about that. I guess that's okay, actually. Now what do? Remember what I want to find, right? All right, so we have two equations and two unknowns. So we could be asked what the tension is, too. So we'll find both. But we were asked what mu is. So we're going to plug this into the other equation, right? Substitute it in. So we would get 866 newtons. But instead of Ft, we're going to put in mu 500 newtons plus another mu times 500 newtons. It just sort of happened to be that way because of angles. And the cosine 60 is 0.5 with one mass of 100 grams and one mass of 50 grams. So that's how those ended up being the same thing. So that gives you 1,000 newtons, right? Times mu. We got 5,000 mu plus 5,000 mu is 1,000 mu. And then divide by 1,000, so mu is 0.866. Now, to get tension, we could come back, and it would be 0.866 times 500 newtons or 433 newtons. If we took a block alone and put it on a ramp without any ropes calculated or connected to it, but just put the block on this ramp with the same material, what would be the angle where it started to move? It just started to move, or move at a constant velocity. Well, mu equals tangent theta, so theta would be the tan inverse of 0.866. That's not asked for, but I'm just saying. (41 degrees). Well, if you go above that angle, you'll accelerate. You'll have a net force and an acceleration. If you're below that angle, you'll have a negative acceleration or deceleration, and you'll slow down. Did the board just flash? Yeah. Mu equals tangent of theta on, like you did for the lab. You just got it to just move. So if we, I guess that's too confusing. So let's look at a force board one. Okay. Yes. Okay, good question. You can't do that because when you do the tangent, it's a specific example. So you can't just do mu equals tangent of 60 because when you raise it up, it's not necessarily going to move. It's not going to move at 60 degrees. Actually, it would be moving, but it would be accelerating. At 42 degrees was the angle that makes it just move at a constant velocity, where the F parallel equals friction. See, but in our case, F parallel did not equal friction. F parallel equal that tension plus friction. That's right. Yeah. U equals tangent of theta. All right. Let's say somebody had a force board like this, 0 degrees. I'm making this up, so I have to think about it a bit. Let's say at 30 degrees, they had three newtons. This was another 30 degrees over here, 3 newtons. And then a downward force of 3 newtons, just for argument. If we find the sum of blue plus red, using components, what do we get? Well, let's see. Let's just calculate it. So we have a I just sort of put my free body diagram right on this because it's easy enough. We have, we'll call it blue Y and a blue X. And we got a red Y and a red X. The blue X equals B cosine theta, or 3 newtons times the cosine of 30 degrees. Two point or 2.6 newtons. And that's negative because it's going off in that direction, right? By, similarly, would be 3 newtons sine of 30, or many of you know what that is, right? 1.5 newtons. Right? Now Rx would be the same, 3 newtons cosine 30, oops, which is 2.6 newtons, but it's positive, right? And Ry would be 3 newtons sine of 30, which is 1.5 newtons, right? So we could see with that if we sum them, so if we wanted to find the sum of blue and red, right? The sum of the x's in the blue give us 0 newtons, right? Why is that? Because minus 2.6, well, if we take the red one, or the blue one we did first, so that was minus 2.6 newtons plus 2.6 newtons, that gives us 0 newtons, right? And then the y's, the sum of the y's would be 1.5 newtons plus 1.5 newtons equals 3 newtons, right? So our sum of the red plus the blue is 3 newtons, positive 3 newtons. Does that make sense? Well, let's find the sum of the blue. Well, sum of blue, gosh, plus green. Well, we already have the blue components, dx and by. The green components, gx and gy, for lack of better symbols, would be 0, and gy would be 3 newtons, right? Minus 3 newtons. So when we sum the x there, we would have minus 2.6 newtons what? Would it be what? Minus 2.6 newtons plus 0 newtons, oops, green, that equals minus 2.6 newtons. When we sum the y's, we have the blue, which is 1.5 newtons, minus 3 newtons gives us negative 1.5 newtons, right? We sum the x's and sum the y's. Now, the resultant would be by Pythagorean theorem of the two, because we would have the sum of the x minus 2.6 newtons, the sum of the y minus 1.5 newtons. We want this resultant. Then the resultant would be the square root of minus 2.6 newtons squared plus minus 1.5 newtons squared. But what happens to the negative when we square it? I'm going to leave it out of the calculator because it doesn't know what I'm thinking. Okay? So I leave the negative out. If not, I'd have to put it in parentheses, parentheses, minus 2.6 squared, close parentheses, plus parentheses, minus 1.5 squared, close parentheses, enter. 3 newtons. Well, it would be exact if I didn't round earlier. So there's a relationship amongst the sum of the vectors, whether it's blue plus green or red plus blue or blue plus red, or blue, well, all three combinations, right? See that? So let's do a hanging one from a sign. We could just make it up. I'm just thinking of who should be on the sign. Let's see. I think I got one. All right, so how about just Tyler's tuning forks? Spoons, too. All right, and we'll have it hanging off with an A of 25 degrees and a B of 65 degrees. And the sign has a mass of 200 kilograms. The maximum tension in these ropes is 3,000 newtons, and Tyler has this guy that hangs out in front of her tuning fork store all the time, drinking coffee, right? And she wants to know if he's in danger of being smushed by the sign. Okay. His name might be Austin, but we don't know. Okay. Maximum tension is 3,000 newtons. Is Austin in danger? Is it I or E? In danger of being smushed. Okay. He was, yeah, he didn't mind. Sometimes I do that, and then I don't realize people take it seriously and they get upset by it. Like I really want to throw them off a building. 2,000 down. Oh, all right. Yeah, let's make it more interesting. I went the wrong way. How about 1,000? Uh, A or B, yeah, just the rope that was hung is 1,000. Yeah. I can't. Yeah. She would say good morning or something. But anyways, let's get to work. We have lab work to do too. Bx, by. Ax, not drawn to scale, obviously. Ay, and then Fg down. Now, in this case, we'll sum the forces in the x and the y. And we'll keep it in equilibrium. So the sum of the forces in the x is just Ax equals Bx. And what do we have in the y? Now we're going to end up with two unknowns, A and B, when we put them in these equations. And then, we are going to substitute actually in A. This is 25 degrees. So we have A. What is Ax in terms of A? Components. A cosine of 25 degrees equals B cosine 65 degrees. You see that? So we took, because here we have four unknowns, Ax, Bx, By, and Bx. So if we put it in the components, then we can get two equations, two unknowns. Ay is A sine 25 degrees, and By is B sine 65 degrees, and Fg is 200 kilograms times 10, or 2,000 newtons. Well, the first thing I'm going to do is find these cosine and sine values. So cosine of 25 is 0.906. Oops. And that equals be cosine 65, 0.422. Over here, the sine of 25 is 0.422. Oh crap, did I do that again? I mean cross, sorry. The 65 and 25 are complementary. That was by accident. 0.906. I think at this point we can see it's not a big deal. So now what would I solve for over here? It's two unknowns. And then what do you do with it? So it's substitution method, right? 0.466. If I divide the 0.906, I get B times 0.466. 0.422 divided by 0.906. Now I can bring that and plug it in for A. Okay. 0.466, I can multiply these two together. 0.197 times B plus B is 0.906 equals 2,000 newtons. Now what should I do? $1.103 times B equals 2,000. Uh-oh. 2,000 divided by 1.103 is 1,100 or 813 newtons. That's the tension in B. Well, it's in danger of breaking. It's only rated. And then A, $845 newtons. So yeah. It could, well, one could break. One's not in danger. Yeah. Oh, then that could break, yeah. And Tyler was seen at the hardware store purchasing a file. What? Why, is one coming? What we do is this. Let me explain it. We shut the door. Okay? Then we would move like your desk in front of the door. Okay? It should be locked. It's not. I'm supposed to have it locked. So I'd have to run and get the keys. Then you have to get down under your desk. Now, however, if in an, well,